we had that NHS meeting and I needed to.
Welcome back, everybody. Is everybody here today? 2, 4, 6.
You needed to bite.
Who are we missing? Anybody? 2, 4, 6, 8. Oh, we're here.
Mm-hmm.
So, hi, Internet world out there.
Mondays I don't play.
I can't wait till somebody like discovers all my YouTube videos, and then I get famous.
Yeah, that would be nice.
Like, I can't wait till I get discovered. That's gonna happen. I feel it.
LA will call.
I'm gonna get signed to a big contract. Take my talents to South Beach. All right. Let's get started. So, in section 4.9, we learned about antiderivatives, right? And it's about calculating the type of function that you would need so that if you found the derivative of it, it would get you back to the original, right? The antiderivative. The antiderivative, working backwards. Anti means kind of like inverse, right? Well, what you don't know about antiderivatives is that they tie directly into areas. Areas. I know it seems weird, like how does that relate? But it does. Antiderivatives tie right in with areas. So that's what we're going to be looking at today and finding the sums of these areas. In this section, we discovered that in trying to find the area under the curve for a distance traveled or a distance traveled by a car, we end up finding a special type of limit. So we're going to focus on two different problems in this lesson, the area problem and the distance problem. Kind of like what we did when we started talking about limits and derivatives as well. All right, so we begin by attempting to solve the area problem, which is find the area of a region S that lies underneath a curve from A to B. That's our goal. Take a curve, find the area underneath the curve. And what do I mean by underneath? That just means that I want to find area given boundaries going from that curve down to the x-axis. Okay, what do I mean by that? That diagram right there. Take a look at that diagram. I'm finding the area underneath the curve from that curve down to the x-axis from an interval from A to B. That curve could be anything. Could be whatever we want it to be. Straight line, quadratic, cube, whatever. Polynomial, could be rational, could be square root, doesn't matter. But our goal is to try to find the area underneath a curve from one point to the next, so from that curve all the way down to the x-axis and stopping there, that bounded region inside there. In trying to solve the area problem, we have to ask ourselves, I love this question, what is the meaning of the word area? What is the meaning of the word area? This question is easy to answer for regions with straight sides, right? It's for a rectangle, the area is defined as the product of the length and the width, right? Just length times width, taking one side, multiplying it by the other side. The area of a triangle is defined to be half the base times its height. The area of a polygon is found by dividing that polygon into triangles, right? So we can also, if it's an odd shape, if it's a weird shape, what we can do is divide it up into things that we can find the area of and add those things together, which is kind of like what we're going to do today. What we do with those weird curved regions that we see down below there. We can take those something easy to find the area of, split all that weird thing up into things that that's easy to find the area of, and end up adding them together in the end. And that's exactly, again, like what we're going to do here. I've got this weird curved shape, and what we're going to end up doing is cutting it up so that it fits into nice, neat little things that I can easily find the area of, and then I'm going to add those things all together. I'm going to be finding a lot of sums in this section, in this chapter, basically. So let's take our first example here. Using rectangles, estimate the area underneath the parabola. The book calls this RAM. RAM. Okay, the RAM. That stands for Rectangular Approximation Method. Rectangular approximation method. Okay? So whenever you see that RAM, just know that I'm using what's called the rectangular approximation method, RAM. So what are we doing here? We're taking x squared, our parabola, our parent function parabola, and we're just taking the snippet from 0 to 1. And we're saying from 0 to 1, let's find the area bounded by the region from 0 to 1 underneath the curve. Underneath the curve. You know, let's try to take it piece by piece. What's the area of that box? 1, right? The area of that box is 1. Is that an overestimation or underestimation? Way over, right? Way over. But I do know that this S area has to be less than 1, right? Okay, what if I take this away? What's the area of that triangle? Half, right? 1/2, because it's half that box, right? So it's 1/2. Is that still an overestimation? Yes. I am accounting for pieces that I do not want, right? This piece in here, I don't want to include in that area. So I know now that I can kind of narrow it down. See, this process of kind of focusing in toward the actual area is what we're really going to be doing today. Here's what I mean. We know that this has to be somewhere less than 1/2, somewhere bigger than 0, but less than 1/2. Right? So what we're going to do is just keep breaking this thing apart. Let's take right in the middle there. What's my x value right there if I go directly in the middle? 1/2, right? What if I take that rectangle? What if I take that rectangle? Because I know this has to be less than 1/2, but I know that it's going to be greater than 0. What's the area of that rectangle? Well, the area down here, the base down there is going to be 1/2, right? The base down there is going to be 1/2. Okay, if the base is 1/2, what's my height? What's my height? Well, what is that coordinate? 1/2 comma what? 1/4. Yeah, 0.25, right? 1/2 comma 1/4. How do I get that 1/4? It's just x squared, right? So if I know what the function is, I can kind of evaluate the function at that point to tell me where it's going to occur. That's 1/2 comma 1/4, which means the height of this rectangle is 1/4, isn't it? So what I can say now is, well, what is the area of that? What is the area of that tiny little rectangle? What's 1/2 times 1/4? 1/8. So now I can say, now I'm kind of narrowing my focus. I had said that the bigger this S, I knew it was going to be smaller than, not or equal to, smaller than 0.5, right? Because I said half of that big box, right? I'm now saying, okay, well, it's got to be still bigger than 1/8. Okay, right? Well, can't I repeat this process, but draw a couple more rectangles? Or in other words, what if I continue with this point right here, but instead of drawing that rectangle into my shape, what if I do this instead? What if I do that instead? Okay, well that 1/4 is here now, right? What's the distance in here? 1/2. So this is 1/2 times 1/4 plus, well, what's this big rectangle? What's my length? What's my full height? 1. Okay, so S is going to be equal to 1/8 plus 1/2. That doesn't really help us, does it? Because isn't 1/2 bigger, or sorry, isn't 1/2 plus 1/8 bigger than 1/2? And I had already narrowed our focus down to 1/2 on the big end. But I still, and the reason why is because I've got all this chunk in here that I don't want, right? I don't want that area. I don't want that area. I want that area to become negligible. So what if we do this then? What if we, instead of doing, let me make that blue again. Instead of making this cut at 1/2, what if we took a couple more rectangles? What if we said, instead of going every 1/2, what if we go 1/4? And each time there saying, okay, well, make a little rectangle here. Make a little rectangle here. Make a little rectangle here. Let's find the area of those 3 rectangles. Okay, now this sum is becoming this. What's the distance in here, though? From 1/4 to 1/2. 1/4, right? 1/4 times, well, what's my height of this rectangle? What's the coordinate? 1/4 comma 1/16. So the height of that rectangle is basically the y value. The next rectangle up, what's the width? 1/4 again. Now, what's my height? Think about this. What's the x value? 1/2. We just did this point. 1/2 comma 1/4, right? We just did that coordinate in there. 1/2 comma 1/4. So this is actually 1/4. This distance here times 1/4. This here is going to be 1/4 times, what's my distance here? Or what's my height here? This is 3/4 comma 3/4 squared, right? Whatever that value is. 9/16, if you will. Okay, let's see what this is. Let's go to my calculator here. 1/4 is 0.25. Well, I'll just do this. 1/4 times 1/16 plus 1/4 times 1/4 plus 1/4 times 9/16. .22, right? 0.22. Put it over here. 0.22. Now, that's on the low end, right? Is that an overestimation or underestimation? An under, because I've got these little pieces in here that I'm not accounting for. So this is still an underestimation. Well, 1/8 is only, oh, that's 7/8, whoops. 1/8, our low end was at 0.125. So I'm actually getting better and better here, aren't I? 0.25 or 0.22. Okay, let's try to keep going from the top end down. Take a look at this here. And I'm going to use these points again. But instead of going over here, Watch what I'm going to do. Hi, Joseph. Yeah. That's the 3 times 6. Multiply 3 times 6 and that's what the whole 4-step process.
If I do it Tuesday, I'm probably gonna do that.
Okay, take a look. Take a look. Take a look. Hopefully this comes out less than 1/2 because I want to keep narrowing it down. Take a look at this new sum. Let's take a look at this new sum, shall we? So what is this now? This is 1/4 times 1/16 plus 1/4 times this here, 1/4 plus 1/4 times 9/16 plus 1/4 times 1. Is this an overestimation or underestimation? Overestimation. Hopefully it's less than 0.5. Or else we're doing this for nothing. 1 divided by 4 times... If you're not paying attention now, this is going to be rough later. I promise you need to understand the baby steps because this ain't going to be baby steps. Divided by 1/4 plus 1/4 times 9/16 plus 1/4. Okay, we're getting smaller. 0.47. 0.47. 0.47. Now, I think you guys can see where we're headed with this. What if I went instead of by 1/4 by 1/8? Instead of just breaking it into 4 rectangles, why not break it into 8 rectangles? Instead of breaking it into 8 rectangles, why not break it into 16 rectangles? Instead of breaking it into 16 rectangles, why not break it into 1,000,000 rectangles? Now, notice every time we break it apart, every time we break this thing apart into rectangles, I have a choice to make. Do I go with, let me try to erase this here to show you what my choices are. See, every time I break it apart, I've got these points. And I'm breaking it into 4 sections, right? 1, 2, 3, 4. I have the choice to make, do I go here and find that area, which would be an under approximation, or do I go here and find those rectangles, which would be an over approximation? So you know what we're going to do here? Go like this. We're going to calculate overs and unders and overs and unders and overs and unders and overs and unders until we know where it's actually going to end up. Yeah.
Why don't you just do the rectangles underestimate the rectangles and then do the triangle on top?
Because it's just unique because this was a triangle. It worked out that way. Because like when I get to things like this, and it's like, right? Is there a triangle to make there?
No.
No. You know? So what we're going to be doing here is breaking it up into rectangles. The rectangular approximation method says that if I break it up into rectangles, that's going to give me two approximations. An over approximation or an under approximation based on how you construct those triangles. Now, would it be safe to assume that I just calculate over and under and cut it in half, find the average of the two? I mean, I guess I could do that. Think about that. What would we be doing if we just found the average of every over and under approximation that we would want to find? You know what that is? That's actually finding these rectangles. It's finding those rectangles in there. Because each of those points is still the height of that rectangle. And I still have the left and right as 1/4 in this case. Okay? But what I'm doing is taking the midpoints of each one. Now, does that get me a good area? It gets me close, but does it get me exact? No. Because is this the same area as this? No. No, it's not. Is this the same area as this? No. Is this the same area as this? And then we're just leaving out that little piece in there? So while it may be very good to get a good approximation by using that midpoint, by using that middle approximation, cutting it in half, is it still equal? Like, can I say that it's definitively must be that area? No. We can't use that. That's why this is just an approximation of what it's going to be. So how do we actually calculate it? How do we actually calculate it? Well, I'm going to show you one way to prove that it's going to be 1/3. And, sorry, spoiler alert, from 0 to 1, from 0 to 1 of x squared, guess what it comes out to be? 1/3. 1/3. Okay. Now, for the region S in example 1, show that the sum of the areas of the upper approximating rectangles approaches 1/3. That is the limit as n goes to infinity of r sub n. Now we got to learn a little bit about the notation. R means right side approximation. Right side approximation. The upper approximation. The over approximation. Okay? This says the right side approximation. You want to know what that means? That means if I take these quarter points in here and I find each one of them, that I make my that length in there is the right side of my box, which means this. Okay? That R means right side approximation. There are 3 types of approximation. R sub n, which is the right side approximation. L sub n, which is the left side approximation. That's the under approximation in this case. And then there's an M sub n. You know what that is? Midpoint approximation, which basically is saying each one of those, like what I drew over here, each one of those pieces is the midpoint. Okay? Now, I don't want to cut this into fourths. I want to cut it into eighths, no 16ths, no 32nds, no 64ths. I want to cut it so that n goes to infinity. Now, think about it this way. If I cut it into fourths, how many boxes do I have? How many little intervals do I have? 4. If I cut it into eighths, how many rectangles am I going to have? 8. If I cut it into 16 pieces, I'm going to have 16 rectangles. If I cut it into n pieces, how many rectangles am I going to have? N, right? I'm going to have n rectangles for my rectangular approximation method. Now, what's the length of each one of those rectangles? What is the length of each one of those rectangles? We'll think about it in terms of fourths. If I cut this into fourths, what is the length of each rectangle? 1/4. If I cut it into eighths, what would it be? If I cut it into nths, what it would be? 1 over n, right? So I can start here by saying this. Well, the sum is going to be equal to 1 over n times, well, what is the height of each one of those going to be? Take a look at my first box. What's the x value here? If this was 1/4, right? If I cut it into 4 pieces, this was 1/4. If I cut it into, If I go to this second place, that would be 2/4, 3/4. I know that's 1/2, but what I'm showing here, this would be 4/4. What's happening to the numerator each time? It's getting bigger by 1, right? So that means that this would be, well, and what's the denominator? 4. So if I cut it into nths, the denominator is going to be n. Now, so that means this is going to be 1 over n, but I don't want just that value. I want that value, because this is x squared, I want that value squared. Right? Because it's the y value. The height is the y value of that point. Okay, the next box would have the same width, but now the height changes. What's the x value on the second box? 2/4. So 2 over n. What's the height on the third box? 3 over n squared. All the way up to 1 over n times n over n squared, which is 1, right? So my goal is to find that sum. The goal is to find that sum. Did you guys work with summation notation last year? The big E? This thing? The sigma? Did you guys work with that last year? That's really what we're doing here, isn't it? I'm finding the sum of all of these little pieces, right? Well, if I really was looking at this, what's common out of all of this? What's multiplied out of every sum? 1 over n, right? So it's got a common factor of 1 over n. So S is really going to be equal to 1 over n times the sum of all of these little pieces in here. 1 over n squared plus 2 over n squared plus 3 over n squared plus n over n squared. Just going to kind of keep manipulating this down. Now, if I distribute that squared in, I guess I could have done this on this next step. But 1 over n, this would be times 1 squared over n squared plus 2 squared over n squared plus 3 squared over n squared plus n squared over n squared, right? That's no surprise. I just distribute that power to both numerator and denominator. Now, can't I pull out a 1 over n squared? Do you see how I'm dividing by n squared to all of those things? So let's pull that out. Let's pull out a 1 over n squared. So S is equal to 1 over n times 1 over n squared times 1 squared plus 2 squared plus 3 squared plus, I forgot my dot in there, n squared. Now, I can multiply in the beginning here and say S is equal to 1 over n to the third. And then we have this sum. Now, the book does a fancy thing. It assumes that you know what that sum is. I'm guessing you guys don't know what that sum is equivalent to. I actually had to look it up when I was learning this last year. You want to know what that sum is actually equivalent to? N times n plus 1 times 2n plus 1 all over 6. That's just the sum of 1 to n. When we square them, that's just the square of sums up to infinity, is also equivalent to that. That's just like a constant. Like that's just something that a lot of people know. I remember learning that in calculus when I was your age. But again, that was like, wow, that was a really long time ago. 35. I learned it when I was like 19, 16 years. Half my life ago. Ooh, long time ago.
Wait, so it's always going to be that? Like in
This
scenario, like
this. That is equivalent to that.
So is that like the 1 squared plus 2 squared? Is that something that we're gonna get often?
If I had you use that, I would give that to you.
Oh, okay.
Yeah. It's like the acceleration due to gravity. You know, it's like a constant that I wouldn't expect you to memorize that.
Okay.
That's a little above your heads.
Okay.
A little. All right, now let's try to reduce that down a little bit. Do you see this here? So that sum is now equivalent to 1 over n squared times, I can cancel that out, n plus 1, 2n plus 1, all over 6. Now this is just multiplication, so I'm just going to multiply that n squared in. This is really just n plus 1 times 2n plus 1 over 6n squared. Oh, I thought I heard it not. Sorry. Y'all done? Okay. Where were you? Who's your teacher there? Do you know? Okay, let me write you a pass. I was going to email that person. Oh, you ripped off my last name. There you go. I wrote my last name.
I understand like going over and under.
All right.
Are you stable?
Okay. Let's pick up where we left off. I'm going to multiply these together up top. I'm just going to FOIL that out. So now my sum is equal to, first outer inner last. We got 2n squared plus 2n plus n, so plus 3n plus 1, all over 6n squared. Now, this is what that sum is equivalent to, right? I want to find this sum where n goes to infinity, right? This is really the limit that I want to find. The limit as n goes to infinity of 2n squared plus 3n plus 1 all over 6n squared. Does anybody remember how the technique to calculate an infinite limit? Anybody remember this? You divide by the biggest. Look at you guys. Go. You divide by the biggest power in the denominator. So 2n squared over n squared plus 3n over n squared plus 1 over n squared, 6n squared over n squared. And we cancel. So the limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared over 6. If I make n to go to infinity, what's going to happen to my two terms with the n in the denominator? Those are going to go to 0. and 2/6 is 1/3. Now, that was a giant problem. One that is very difficult, right? I think you guys would agree that that was no cakewalk right there. Calculating the sum of that, the limit of that sum was pretty difficult. I will tell you, just so you see some foreshadowing here, antiderivatives will do that for you. Okay? Antiderivatives will be calculating those sums for you. So remember when we would find the limits of those big things and then like in chapter 2 and then we were like, oh wait, here's all the rules for derivatives?
Yeah.
It's kind of like the same thing. We're going to have to go the long route until we see how antiderivatives work.
Skip. Let's just skip it.
Let me show you something. What function were we working with at the very beginning? X squared, right?
Yeah.
Yes.
What's the antiderivative of x squared?
X squared.
Or
X to the third.
3. Oh yeah, sorry. X to the third divided by 3. Where did we go to? We found the sum between 0 and 1. You see that? I know. I just want to show you, I just want to tell you, it'll get better. We will get to the point where we can use this. Yeah. But for right now, we kind of have to learn the building blocks before we get to the fun stuff. Okay. We'll pick this up tomorrow.
That stuff that will be fun after doing all of this.
I know.
Why are we doing it?
Because you can appreciate it.
Is that like an example of what would be on the quiz?
It builds character.
Okay, Dad.
It builds character.
I appreciate it for that one problem.
That's it.
I don't need to do any other problems. I already appreciate it. That's appreciated. Like, we get it. Okay.
You have to review our review or
I can. You want me to post it right now?
yeah, that would be
Yeah.
great. Thanks.
If I don't do this right now, I will forget. So, I'm still rolling. Still rolling.